So let us continue with the further singularities, poles, and now Cauchy's residue theorem. I just say simply CRT for convenience. I'll use CRT for Cauchy's residue theorem. The theorem is like this. If C is a closed curve and Fz is analytic, it should be analytic at a finite number of points. At finite number of points, namely Z1, Z2, and so on, Zn. I have a finite number of points. Of course, they are Fz is analytic at these points means Z1, Z2, Zn are singular points. That is, singular points. And not only that, these Z1, Z2, Zn should lie either on the curve on the curve C or in this C, inside C. Then only we can apply this Cauchy's residue theorem. So we have a closed curve, we have analyticity at Z1, Z2, Zn, and we can calculate the residues for Z1, Z2, Zn. In the previous slide I have shown that. And now, then after this hypothesis, then integral over C, the closed curve, Fz dz is equal to 2 pi I. I'm looking at the residues at Z1, Z2, Z1. So I'll simply say res Fz at Z1 plus res Fz at Z2 and so on res Fz at Z equal to n or Zn. So this is simply 2 pi I and some of the 2 pi into some of the residues of Fz at the singular point Z1, Z2, Zn. Just before calculating the residues and before applying this Cauchy's residue theorem, let me do a problem which will be very interesting. Z square by, consider Fz is equal to Z square by Z minus 1 whole square into Z plus 2. Look at carefully about the function. I have to calculate the residue. I want to apply Cauchy's Riemann residue theorem. So look at this Fz. The zero, simply all the times I will calculate the zeros of Fz. Zeros of Fz are Z minus 1 whole square. So Z equal to 1, a pole of order 2, because Z minus 1 whole square into Z plus 2 is 0. So Z minus 1 whole square is 0. So Z equal to 1. It is repeated. It is a pole of order 2. Then what about this? Z is equal to minus 2. Now, I want to calculate the residue. So, residue of Fz at Z equal to 1. This is equal to, because it is a pole of order 2, I have to apply m is equal to 2. As in the case remark 2, I have done m equal to 2. So this will be 1 by m minus 1 factorial, m is 2, 2 minus 1 factorial, 1 factorial, limit z tending to 1 because this is a singular point, and then I have to write down m is 2, so d by dz of, it's a single derivative of z minus 1 whole square into fz, z square by z minus 1 whole square into z plus 2. All the times I'm again and again repeating this because this has to be cancelled. Whenever I am talking about any residue, when I was talking about the residue, I am looking at the singular point. Also, that singular point z minus 1 factor should go out. So this you have to cancel. Is equal to 1 by 1 factorial is 1. Simply limit z tending to 1. Now, the derivative of z square by z plus 2, apply the quotient rule. You have z square by z plus 2. So, quotient rule, derivative of this is z plus 2 into derivative of z square is 2z minus z square into derivative of z plus 2 is 1 by z plus 2 whole square. It's fantastic. I have to simplify this with z tending to 1. So 2z square plus 2 into 2, 4z minus z square by z plus 2 whole square. I need not simplify by writing 2z square minus z square plus 4z because the factor z minus 1 whole square has been removed from the function, from the calculation. So simply I can apply z equal to 1. If I apply z equal to 1, I'll get 2 into 1 plus 4 into 1 minus 1 by 1 plus 2 is 3 square. So this 5 by 9. So the residue of fz at z equal to 1 is 5 by 9. What about the fate of z plus 2? Z equal to minus 2. It is a simple pole. Z equal to minus 2 is a simple pole. So, what I have to write down is, I will calculate the residue of fz z equal to 2. Residue of fz z equal to 2. This will be simple z equal to 2, so limit z tending to, this is minus 2, so z tending to minus 2. Now I have to remove this factor, so z of minus 2, which is plus 2, by fz is z square by z plus 1 into z plus 1 whole square into z plus 2. So I can remove these two again. Now what I have left over with z square by z plus 1. Z is tending to minus 2. So this is equal to minus 2 whole square is 4 by minus 2 plus 1 is 1 by 1. So we'll get plus 4. So evaluate. Integral C z square by z minus 1 whole square into z plus 2 dz using Cauchy's residue theorem, using CRT. Let us look at the zeros. The zeros of fz are z minus 1 whole square, so 1 and 2, where 1 and minus 2, where 1 is a pole of order 2 and minus 2 is a simple pole. So I want to evaluate the integral by using Cauchy's residue theorem. So residue of fz, z is equal to 1. Now I will make use of this remark 2 for calculating z equal to 1, because it is a repeated pole. So here m is equal to 1, m is equal to 2. It is a pole of order 2, so m is 2. I'll write down 1 by m minus 1 factorial, limit z tending to 1, and z minus 1 whole square. Of course, I have to write down the derivative here. Limit d m. M means 2, 2 minus 1, 1. So dy dz of z minus 1 whole square. Fz is z square by z minus 1 whole square into z plus 2. The only technique is all the times we have to remove the factor which goes to 0. Z tending to 1. So z minus 1 tends to 0. So that factor has to go out. This is limit z tending to 1. Now the derivative of this function is z plus 2 into derivative of z square is 2z minus z square into derivative of z plus 2 is 1 by z plus 2 whole square. This is equal to, simply I can substitute without simplifying this, because if z tending to 1, I have removed the factor, so that will help us. 1 plus 2 into 2 minus 1 square by 1 plus 2, 3 square, which is equal to 2 plus 1 is 3, 3 plus 2 is 3 into 2 is 6, 6 minus 1 is 5, 5 by 9. What about the residue of fz for z equal to minus 2? Because it is a simple pole. Limit z tending to minus 2. Write down z plus 2 because it is z tending to 2. So z minus minus 2, z plus 2. Limit of z plus 2, z tending to minus 2 into fz. Fz is z square by z minus 1 whole square into z plus 2. I have to get rid of this z plus 2 because it's tending to minus 2. So I have z square by z minus 1 whole square. Now z equal to minus 2. So what I will get? I will get minus 2 whole square by minus 2 minus 1 minus 3 whole square, which is again 4 by 9. I have calculated the residues. But if I want to apply Cauchy's residue theorem, I need the poles should be inside the curve. So I just calculated now I have to give some more information on this. Using CRT theorem with the mod z equal to 1, suppose if I say this, that means it is a circle with radius 1, center 0. Now, if you look at 2 and minus 2, if you look at 1 and minus 2, 1 will be inside the or on the curve or on the circle, whereas minus 2 is not in C or on C, on the curve. So minus 2 cannot be a choice. Hence, I have to take only one residue, which is residue of fz, z equal to 1. That's 5 by 9. So, hence, integral mod z equal to 1. I am writing this. Sometimes people write over C when you understand that. Fz is z square by z minus 1 whole square into z plus 2 dz is equal to 2 pi I into sum of the residues, but there is only one residue which is 4 by 9 because the residue of the 5 by 9 because the residue of z equal to minus 2 is not a candidate. So 2 pi I into z equal to 1 I have to write down 5 by 9. So 10 pi I by 9. Evaluate integral over C z minus 2 by z into, I can write down any other function which is not analytic at that place. So z into z minus 1, I can write down z minus 1 or z minus 3, whatever it may be. This is only where C is mod z equal to 2. That means it is a circle with the center 0, radius 2. So the zeros of solution is the zeros of fz are 0 and 1. Both are simple poles. Both are simple poles. Mod z equal to 2 means it is with a radius 2, with center 0. So both are in C, 0 and 1. Hence, we can calculate residue of fz z equal to 0, which is limit z tending to 0. I have to take z minus 0. Fz is z minus 2 by z into z minus 1. I am repeatedly saying that this has to go out. So if z equal to 0, I will get minus 2 by minus 1, which is 2. What about residue of fz z equal to 1? This is limit z tending to 1 limit z tending to 1 z minus 1 into z minus 2 by z into z minus 1. So z minus 1, they go out, is equal to, now z equal to 1. If you put z equal to 1, this will be minus 1. So the residue is 2 and minus 1. The residues are 2 and minus 1. Thus, by CRT, Cauchy's residue theorem, what I have is integral mod z equal to 2. This is a way of writing sometimes. Mod z equal to 2, z minus 2 by z into z minus 1 dz is equal to 2 pi I into the residue of this plus residue of this. The residue of this is 2 plus this is minus 1. So you'll get 2 pi I. That is the integral. And at another simple problem I would like to discuss is evaluate integral 1 by z sine z dz over C. Now I have to specify what that C is. 1 by z sine z with mod z equal to 1. With mod z equal to 1. Let us see the zeros. You can write down z equal to 0 and sin z equal to 0. So you will get sin z is 0 means again sin z is sin 2n pi I. So n is 0. So you will get that way. But anyhow, I can write down z sin z equal to 0 implies, let me do one thing, z into, let me expand sin z. The series of sin z is 1 by z minus z cube by factorial 3 plus z power 5 by factorial 5 and so on equal to 0. Take z common. So if you take z common, you will get z square into 1 minus z square by factorial 2 so on is 0. So this 0 means z equal to 0 is a pole of order 2, is a pole of order 2. So let us calculate the residue of fz at z equal to 0, which is equal to 1 by 2 minus 1 factorial, that's 1 factorial. So into limit z tending to 0, d power d by dz, because m equal to 1, so this into z minus 0 repeated, so z minus 0 whole square, which is z square, because z minus 0 is a pole of order 2, so I have to take z minus a whole power m into, what is dz? dz is 1 by z sine z. Again cancel these two. So I have, this is equal to limit z tending to 0. If I simplify this, sine z into derivative of z is 1 minus sine z into derivative of sine z into derivative of z is 1 minus z into derivative of sine z is cos z by sine z square, sine z whole square. Find the limit. Use L'Hospital rule, because sine 0 0, cos 0 is 1, this is 0, so minus 1 by 0. Again you will get, so if you use this, if you calculate the residue will be simply 0. This will be 0. So what is the integral? Now I have the integral. So sine z minus z cos z, if you evaluate, that is 0. So the integral 1 by z sine z dz over the circle C mod z equal to 1 is equal to 2 pi I into residue is 0, which is 0.